And then when 0 minutes left, I'll stand up. We'll have some stronger time.
No, that's totally fine.
You know, 1 year.
Yeah, I think.
Hello, everybody. Welcome back to the second lunch of the morning. My name is Reiners. I'm sharing the section. Is this background? You get any background? Okay. So we're going to get started with our first talk for this section. Ansgar Reiners.
Magnetic fields are the root cause for most of the exciting phenomena that we are here for and that have been the reason for the Cool Star series for many decades now. However, it's very difficult to get direct information, immediate information about how they are being formed, how magnetic fields come up, and how magnetic energy is actually being produced from some other type of energy. And what I will try to do for the next 20 minutes, 25 minutes, is to show you at least my personal view of about what we know in terms of direct information, or the most direct information that we can get about this game. And it's actually true that this never works when it's needed, because we checked it before. But this is because this doesn't work at all right now. So, okay. No, it's on. Okay. So you all know this, and I want you to focus on this thing down here. This is the magnetogram. So if we look at the sun as the sun, we can see the polarity of the different magnetic fields, and they of course coincide with the visual information. They coincide with all the chromospheric coronal lines that we have. And from this, we already know that anything that is going on the sun that is not boring is magnetic, right? And mainly also that magnetic fields are the cause for all the different phenomena that we know and that are important for SPI, star-planet interaction, or the evolution, and then it goes into the rotation, and what have you. We know all this. I won't go into any of the details. I want to start with this plot here that is a bit more than 2 decades old. This shows you the direct relation between the X-ray luminosity of different pieces, of different surface features on the sun, together with their magnetic flux, which is R squared times the field density B, the flux density B. And then it continues out here into the stars. These are Titori stars here, and these are some GK-M dwarfs, what has GK and M dwarfs, what has been known at the time. And this diagram has been very influential, and I think it is very important, showing us how X-rays directly correspond to magnetic flux. And one of my missions today is to give you some stimulus to think about these kind of clear relations and whether they actually tell us as much as we think. Because what we see essentially is that R squared is proportional to R squared, which is a nice thing to prove. But if you take this out, it would be much better if we could take this R squared out here and this luminosity as well, and then we learn something about how the fields really connect to the X-rays. And I will try to do this later with what kind of information we have. So don't get me wrong. I'm not saying this is not a useful plot. This is one of the very influential plots of this game. But I want to remind us all that these relations spanning over so many magnitudes, spoiler, over those many magnitudes, sometimes they do have much more information than what we sometimes appreciate. So let's look into the rotation activity connection. This has been done a few times. I prefer this plot not only because I made it, but also because it looks so horrible in colors. Shows you that the rotation activity relation actually holds for stars of very different ages and very different masses. It is the normalized X-ray luminosity, now taken out, the L bar was taken out, as a function of the Rossby number. And the first thing I want you to see, so what we all know, I suppose, is that there's some rotation activity connection here, and there's some sort of saturation up here. Now, the first thing that we need to realize, and that is not really appreciated often enough, is that the area where we have the rotational influence is where the stars are rotating slowly. This is not really what you would expect from dynamo theory. You would expect that the rotation is more important the faster the star rotates, at least if you ask some of your friends who are doing dynamos. Not all of them may tell you this. But if you are in the regime where rotation is dominating, this correlation actually breaks. There is saturation. And you can show that in this diagram here from these many data points, there's still a small slope, but this is not so important here. Now, why is it that we always show this diagram? Rossby number. I tell you my story, or I tell you this story, and with a few side words. The Rossby number, any kind of Rossby, any kind of dynamo scaling that you expect with rotation goes with the ratio between the rotational timescales and the convection timescales, because the energy is in the convection. So there's P over tau, and tau is the convective turnover time. What is that? It's the time you need to actually sort of go around in your convection zone, and we really have no good clue what this is. And also, this idea that this rho works comes from a solar type dynamo with differential rotation that is proportional to omega over d, and d is the depth in your convection zone. And then you get out some dynamo number that goes proportional to exactly this number rho. So if you do this for your star and you calculate the turnover time, you have to ask yourself, where are you? And then from a theory argument, this doesn't really make a lot of sense. In particular, not if you cross the fully convective boundary, because then this thing here is definitely completely different. So it may be the right thing to do things, but most probably for the wrong reasons. At least this is what I believe, and what I'm trying to say is that we should try to understand what we do here with a fresh view. So what people have done already, again, more than 20 years ago, is to find the right scaling of tau to make this theory work. Okay, so to say, yes, this is solar dynamo theory, and this brings out this nice plot here. And if you do this, you find out that the convective overturn time is simply 1 over the square root of the bolometric luminosity, which is much nicer than any kind of B minus V or whatever observational colors fit you can have. Because this is simple, this is a very simple physical entity, and this is as old as this paper, this information here. And again, now we realize something that we've realized before. If you put the L ball here, and actually if you look at these exponents, and so you get some squares and stuff. So there's one, you end up with something that is proportional to 1 over L ball here, and there's a 1 over L ball here. So what we've done is we've been cheating against ourselves and putting L ball on both axes. And we could have done this in a much easier way, probably. I'm not saying that an easier way, plotting it in a different way, is more correct in a physical sense. But we have some observables that we can actually put together in a much cleaner way, and that's this way. We can say, and I go back, buckle up here. We can say that here, what is happening is that we are saturated at the ratio of Lx over L ball, about 10 to the minus 3, and we can keep that for the saturated part. But for the non-saturated part, we can actually say that Lx is proportional to P. And it turns out that the scatter around these cloud of points is smaller than if you plot it the other way. So the problem is that I have no explanation why, right? So what comes out is that the stars here on this end, with a rotational period P, regardless of what their mass is, what their radii are, and whatever, they all end up with the same amount of total luminosity in X-rays. P sets Lx. That probably makes no sense. I don't know. Some people have ideas about why that could be. I don't really know whether that's right or wrong. Just all I'm saying is here is if we try to understand it this way, at least we have the observables right, because everything that we have on this diagram are observables. And then we can start with introducing tau or what have we, or other more or less useful units that we can add on the x and the y axes and try to understand the physics. But this is a very clean diagram. And the idea here is, and now we come to a question that has been asked yesterday, why is 3 days so important in the sun? Why is the sun saturating at 3 days? And the idea here would be that if you are a slow rotator, you would live somewhere down here where p is proportional to Lx. And if for some reason you crank up the velocity, you produce more and more Lx's until some time where Lx over L ball reaches this critical value of 10 to the minus 3. And then I plot you up there, okay? So, and for the sun, magically, 3 days is the time that happens. So that's the saturation velocity. For other stars or other masses, this happens at different velocities. And why 3 days? Of course, I don't really know. It could also be other days, but this is the observation here. So here you are depending on p, and at some point you are saturated. And why are you saturated here as at x over L ball? Here, one idea is that this could go together and could be explained by some sort of a geodynamo model, where essentially the idea is that the saturation kicks in because the convective energy scales with the luminosity, okay? So we have a convective star, the outer convective envelope is producing all the luminosity that we see, essentially. It's a convection zone, that's the definition. So essentially what we see is the amount of convective energy available, and that must be a limit for the magnetic energy you can produce. I admit that the units here, this is convective energy flux, and this is energy. This is not really comparable, and this whole argument needs a few more steps, but I only have a limited time. So you can see here that this, at least in this plot, it works for these amounts of points, and there's some brown dwarfs that are upper and lower, and there are some ideas that this may not work everywhere, and there are, of course, other ideas that it's completely wrong. But at least this is one explanation why we see the saturation at the level we see it. And then these 3 days just come out at where the sun actually reaches that point. Part 2 of my talk, I will be really brief here because there's a session today in the afternoon about how we measure magnetic fields. And I only want to point out the very basic misunderstandings that you can have in magnetic field measurements and if you read the papers. And therefore, I'm going to skip over it really fast and go to the physics later. So we have 2 methods here in visible or infrared light. We can investigate polarization, or we can investigate non-polarized light. If you have a spectral line without a magnetic field, you have 2 energy levels, spectral line, and if you have a magnetic field. In the ideal case, everything splits up into these 3 components. You have a pi component in the center and 2 sigma components right and left of it in the spectrum. And then you can see this triple if you really are spot on your magnetic field. And from this, you can play your games, and I will show 2 more slides later. But before I do this, I want to introduce the third method that we have also heard about a little bit. That's radio emission at some frequency nu. And that happens because of mostly of gyrosynchrotron emission in some case. So you have a magnetic field somewhere, maybe here, and then electrons are moving. We don't know where they're moving, but at some field strength, they are doing cyclotron motion. And in a uniform field, if that is available, electrons can do this move. And then you receive the cyclotron frequency, and that is exactly at 2.8 times the magnetic field. So this can be used to probe whether anywhere on the star where you have enough electrons, you have a field that is as strong as this if you are measuring at a certain frequency. That does not really tell you much about the average field of the object. Okay, this is very, very powerful to measure local magnetic field strength, and an enormously useful method. It is difficult to get the average field strength or do any predictions about the average field strength of an object from this method. To be quick and to confuse you a bit, if you are not interested in polarization, you can snooze in for 3 minutes, but I'll wake you up again. So we have a magnetic field here, and we have these 3 components, 1 pi component, 2 sigma components. And depending on from which direction you look, perpendicular to the field or transversal, you can see the 3 components, the sigma component, the pi component, or here only the 2 sigma components in different states of polarization. Only if you look into that direction. And then you can construct these nice little Stokes parameters. Only one of them is the addition of 2. and all the others are more or less complicated differences, of course. And then you can, and these are things you can measure with one more or less complicated methods. And what turns out, and I'll really skip over this very fast. This is what you see here on the left is a yellow circle with a few other circles. This is not really a star, but it's meant to be magnetic field areas on a surface that have different polarity depending on the temperature. Depending on that and depending on the angle you look at it, you see different field strengths. Okay, so if you look at Stokes' I, you always see a broadening pretty much because this is an addition of the different polarization states. If you look at Stokes' V, you don't see anything if you look like this. And if you look at Stokes' Q or U, you have a lot of information in this part. And now this was transversal. This was perpendicular. This is longitudinal here. So you see the Stokes' V component is very strong. And one more take-home message, I'm not going to introduce this in detail. One more thing is if you have two field areas that are canceling out each other in terms of net flux, you actually see nothing in Stokes' V. So there's potential for confusion. That's all I'm saying. And there's a lot of information about the geometry from polarization. And polarization is a differential method. That means it's a lot more sensitive than what we could get from Stokes' I without knowing the lines themselves. So if you want to model this, if you want to model the field on situation versus the field off situation, you need to know how the field off situation looks. And it's not so easy to get. So you need to understand that. In Stokes' V, you don't, because it's a differential method. So that's much more powerful on that end, but it comes with a few caveats. And of course, from Stokes' V, you can do a lot of information. You get all these maps that we've seen before. And I just wanted to acknowledge this here. Okay, last part, and most important, I think. So I guess one of the main reasons I'm here for is to introduce you to a study that we've done. We, from the Carmenes team, and this has been introduced a few times, have built a spectrograph that has the sole purpose of the spectrograph is to show you all the nice magnetic field measurements today. Okay, we found a few planets on the way. Okay, but really, this was done. We surveyed 300 M dwarfs for many years, looking for. Some people looked for planets with the spectrograph. I admit that. But then you can take all the data, 15,000 individual spectra, and correct them for telluric lines, and use some code to actually model the field lines. And I would like to acknowledge the work of Oleg Kotchikov as well, who's also one of the people behind the code that has evolved through different generations, and that was finally used also for many things, including this work, together with Dennis Shuliak, who's here on the paper. And from that, we have measured magnetic fields from Stokes' I, which is the method where you can get the most, I think, the most accurate information about the total average field. That doesn't mean that the error bars are small. It just means that we are not missing a lot, most probably. And how this works, what we've done here is this. For one star, for example, we have a number of lines. We have very high singular noise, quite high resolution, 80,000, 90,000, depending on the wavelength range. And we have here, for example, the best fit we get with no field and with a field. And from many lines, you can get useful information about the underlying field. And just to show you that in the age of today, even I can use MCMC, and I can get things like this. So for this particular star, we get a distribution like this, and you can see how things are degenerate. Of course, there are some degeneracies between different things under the assumptions that we make. But at the end of the day, we measure the fields for these stars. And we also have some information about the field distribution. So how this plot answers the question, how much of the surface of the star is covered with what field density, like here. And so we have this for all the stars. And now we can look at this plot, for example, and see where are the field strengths, where are the stars magnetic. This is the famous rotation mass diagram. I want to highlight this gap here. That is, of course, not a result from our study, but this is from all the rotation period measurements. So the stars, very low mass stars, they happen to cross this gap here very fast, and it's a very interesting question why. And I want to emphasize that if you draw such a plot, and if you want to plot here regions of constant Rossby number it is a big difference whether you use anything that has come up from B minus V fits or something, or if you use for this 1 over L ball square over L ball scaling that has been shown to at least work in most of the stars. So of course, it may not be correct for all the stars, but I suppose this is sort of the best direct information that we have. And if you do this, you get straight lines here. And they actually coincide. This rho over 0.1, rho equals 0.1, which is sort of the saturation range, coincides with this virtual envelope that you can draw here that sort of goes there. And you can see that the size of the symbol scales with the field strength, so you already see what's happening. This is scaling with the Rossby number as we know it. And before we attend to that, I want to show you the non-thermal heating that comes out of different lines that you can measure in different lines, including X-rays, as a function of the magnetic flux. This is the same diagram as we've seen at the very beginning, where I said that R square is proportional to R square, so you can make the same argument here. But we see very clearly that in our sample, there's a really clean correspondence between magnetic flux and all the indicators that we have. So, and from this, you can actually attempt to predict the magnetic flux if you have any of these indicators in any useful way. It doesn't really need to be very accurate, but within reasonable ranges, you can make that prediction. If you want, you can look at these equations, but this is where we are in the diagram from Pevtsov et al. So we are a bit below that. And maybe this was already appearing here with the other symbols, but maybe not. So we are not exactly on the line. We're somewhere below. Whether that makes any difference, I don't really know. But we can now do the exercise and divide out R square from both axes here and look what the normalized emission does as a function of the magnetic field. And here we can now really see at which magnetic flux density on the stellar surface X-rays, H-alpha, or calcium emission are being generated. How much magnetic field, how strong a field do I need to actually produce emission? And I find that calcium emission is produced at fairly low fields here. H-alpha is produced, you need a kilogauss more or less to do that. And for X-rays, it's also, well, somewhere a few hundred gauss. Calcium seems to, if you want to believe me, seems to saturate somewhere here. So this line is not going up there. This may be a sign of saturation, maybe not, but this is sort of what I see here. And this is not what you would expect from some ideas that magnetic field are being produced in the faster rotators and generate this non-thermal heating. And the faster you rotate, the earlier you strip your corona. If that was happening, then you would lose X-ray emission. This would go down. Calcium goes down. Calcium is produced in the transition region or somewhere around it. So if you lose calcium first, that is not coronal stripping. I don't know what it is, but it's not coronal stripping. Okay, and here's the money plot. Here's the magnetic field rotation relation. That looks pretty much, well, there's some scatter, of course, I admit that, but that's what we have. That looks pretty much like the rotation activity relation that we know. And well, it's probably not very surprising, but I think it's a big step that we can explain this diagram here by its physical cause, which is the magnetic field generation. Okay, so I think we're closing a gap here with this diagram, and we're opening many more questions because there's certainly more scatter here than you want. So there's certainly some mass dependence that goes beyond what I've tried to explain with this luminosity thing, and maybe, of course, there are measurement errors, but I believe there's some mass dependence here that we still need to take into account, and that certainly lead to the fact that if we use this relation that we get from this, if we use this relation for very low mass stars, we are off. So for Proxima Centauri, for example, if we predict the field for Proxima Centauri from its rotation period, we are off by a few. I want to make a connection to Stokes V measurements, to the beautiful work that has been done for many stars, because we've seen that many times. This diagram also exists for for the B measurements from polarization, from the paper from Alini Vidotto, who gave a talk about other things in the Sprinter. And this is how how that looks. So I had to squeeze the diagram a little bit to make it fit. So you see the same relation down here, and then you see different groups of stars. I don't go into details which they are. These are mostly M dwarfs. And of course, it's always below what we see in Stokes' eye, and by a factor of magnitudes. Okay, but here it's more or less consistent. And this, of course, can tell us a lot about the geometry. And it tells us a lot about how much we are missing if we are looking into these images. Now, this is the final plot that makes the transition from our rotation activity relation that was plotted as a function of Rossby number now into the regime where we are using observables. We are using the rotation period here again. And the idea is that the rapid rotators up here, they are saturated because the ratio between the field that we see and the amount of energy available from convection is about 1. So everything you have is going into the field, or everything that can go into the field. This is sort of a normalization here that we've done to make this 1, of course. And then we have a rise here where the flux actually scales with the rotation period. And this seems to be sort of what's happening on these stars. If your dynamo model can predict this, at least it would be consistent with what we found here. Then you can make the test whether this works with the so-called MAC method, or MAC idea that Coriolis buoyancy and Lorentz forces need to balance each other. For that, if that is the case, you would expect a clear correlation between magnetic energy and the ratio between Akin and rho. For the blue ones, I don't know if you see that, and this is more for the experts because I'm coming to the end here. And my summary slide is this. Convection is dominating stellar magnetic activity. And I want to point that out because everyone says it's rotation. Yes, it's rotation, but rotation is not the source of energy, and rotation is not sort of going into magnetic energy. Rotation is making it possible for converting convective energy into magnetic energy. We have a clear proportionality between coronal and chromospheric heating to magnetism. And we have very different results. We need to be very careful if we compare the results from different methods among each other about magnetic fields. Thank you.
Question answered, to introduce themselves, and for the speaker to repeat the question.
Thank you. Great review. Complicated from as well. Regarding the emissions you showed, the X-rays and H-alpha, would it changing the height of the chromosphere transition region explain this?
So the question was whether the height of the different regions where these emission lines are being generated could between chromosphere and transition could explain could explain the change. By change, you mean the absolute numbers here, or?
Yes.
Yes. I don't know. I think how much energy you really put into the lines is, I would think, has more factors than just the height. But this is certainly a factor. So yeah, the density goes with the height. Good idea. I think I think there is a point to make this study. Yeah. Thank you.
Yeah, thank you very much for this data set. But the data set includes both fully convective and partially convective. Are they different, or your data set both can be adapted?
Yeah, the question was whether we see any differences between fully convective and not fully convective stars. And mass goes with here is symbol size is mass. I've looked many times. I didn't see any reasons to believe that there's something strong, something strange happening on the convection boundary. Now, there's a lot happening on the convection boundary, And I'm certainly not claiming that there's nothing happening. It's just that we don't really convincingly see it here. So everything that I've said is consistent with the assumption that there's nothing happening. But the sample of nothing, well, we go down to fairly low mass stars. Well, the observational biases are different. So there's still, my conclusion from this is that first order approximation, there's nothing to see. But this is not a nice relation. I would like this to be a lot smoother, and I've spent a lot of time trying to make this better, and I didn't find a good way. But there's certainly some mass dependence here. Something weird is happening. It seems to get steeper with slower mass stars, but I don't know if that's true. So, and maybe that is because of, I don't know what, maybe it's the convection boundary.
And that's all we have time for. Sorry.
Oh, works. Yeah,
Sounds great.
cool. Thanks.